We have homework due tomorrow, right? Homework 6, that is. There's 2 567 problems on it, right? And then I think 4 for everyone else. Lab 4 is up, so that's due on the 17th as we discussed. We will have 2 more homeworks, one due next week, one due basically the last day of class. The one next week will be a bit shorter than normal so that you have more time to do work on Lab 4. I contemplate having no homework due next week, so you had all week, but I think that would create problems actually. As much as I want to be generous and do that, the homeworks are going to like fall really far behind the lectures, which is I think they should be more in sync. So anyway, I'll split the difference and we'll have a shorter homework 7 due next week. Homework 8 will probably be a little bit longer than normal. I'll hand it out early, and because you'll have the partial week for Thanksgiving and then the week after to work on that. So that's the homework plan. So homework 6 due tomorrow, shorter homework 7 due next week, and then a longer homework 8 due the last day of class. And of course the projects. I know someone asked on Piazza when the Lab 5 will be due. I didn't have a chance to look that up. That's dictated by the university, or it used to be anyway. I haven't looked up whether it still is. So anyway, we'll sort that out. It'll be well after classes end, during the finals period. Someone brought a notebook up to me at the end of class last time. It said 467. It didn't have a name in it, at least that I didn't see. It was someone's notes. Is anybody here? Is it your notes? I actually didn't bring it with me. It's in my office, so maybe it's better that the person didn't show up anyway. Okay. Anyway, I'll make the announcement again. If you know of someone who lost a notebook, then tell them that I have it. All right, that's all for announcements. Any questions? You good? Okay. So today I'm hoping to finish up coding for the binary erasure channel. The binary erasure channel is this construct we have to help us understand coding, which is in a sense how you map bits to channel inputs in a way that makes them recoverable from the noise. So I guess one way of thinking about what we're doing here is that we spent quite a bit of time talking about how to encode bits into channel inputs in a way that the ISI is easy to recover from. So the channel kind of smears things together because of ISI, and we want to encode the bits in a way that's kind of easy to undo all that smearing. This is sort of a different thing. Okay, the channel also has noise. Okay, and you like to encode the bits in a way that makes it easy to recover from the noise as well. Okay, and it's a slightly different problem. It's a different phenomenon, has different solutions to it. So we're focusing more on that here. And the phenomena are a bit subtle and a bit complicated. And so it's helpful, I think, to work through it with a very simple channel like this binary erasure channel first before we start talking about Gaussian channels like the ComCloud. Okay, so I'm hoping to wrap that up today, the binary erasure part of it, and then starting next week we can talk about coding for more sophisticated channels like ComCloud. So recall the binary erasure channel. This is a channel, it's digital input, digital output, discrete time. And at each time step, the encoder feeds in 1 bit, and the decoder then either receives that bit or the special symbol E for erasure. And the channel erases each bit with probability epsilon, independent of all the other bits. Okay, so if you send in 2 bits, then they can both be erased, neither one or the other, and each is erased independently of the other one. So you just kind of run this. You can imagine just like flipping a coin that comes up with probabilities heads. Comes up heads with probability epsilon, tails with probability 1 minus epsilon. You just flip this coin independently to decide whether each bit was erased or not. So we like to understand how to communicate over this channel, like how do I encode bits, data bits, into channel inputs in a way that the noise, okay, the erasure pattern, can be recovered, or is recoverable from, okay? So the way we'll think about it is, suppose you have k bits, k data bits that you want to send. And you get to use this channel n times. Okay, so you have a string of length k bits that you want to send. Okay, you're going to use this channel n times. After n time steps, the decoder then has to try to guess the k bits as best it can. Okay, and we talked about strategies for that last time, especially if you have feedback. So if you have feedback, you can imagine you just view your k bits as being in a queue. You take the bit at the head of the queue. You just keep sending it through the channel until it gets through. Then take the next bit out of your queue. Just keep sending it until it gets through, and so on. Okay, it can happen that you clear all k bits by time n, in which case the decoder will have no ambiguity about the string whatsoever. It can happen you still have bits left over, in which case the decoder is left to just guess those bits. This seems a little bit contrived, I realize. Okay, in reality, you probably would keep transmitting until all the bits get through. Like, why would you stop prematurely? But the coding phenomenon we're talking about here is kind of easiest to see if you just view it as this like fixed length scenario where like time n you just have to stop. and whatever hasn't gotten through, and try to minimize the chance that not all your data is recoverable at the decoder. Okay. So the scenario is you have k bits, you map it to n bits that go into the channel, some number are erased, and then the decoder observes the channel output and tries to guess the k bits. Okay, and we looked, for the case with feedback, we looked at this kind of asymptotic result, this scaling result, where k and n were both really big. So you have a lot of bits to send, but you have a lot of time to do it. Okay, so they're both big, okay, but their ratio is held fixed at some data rate r. Okay, so k over n is the naturally interpreted as a data rate, right? It's like how many bits you're sending over how long are you taking. Okay, so it's like bits per sample or bits per channel use or whatever. Okay. Okay, so consider the regime where those are both big. K and n are both really big, but this ratio is held fixed, so they're both kind of growing proportionally to each other. Okay. So we showed last time is if r, the data rate, is below 1 minus epsilon, okay, then this error probability will go to 0 in this limit. Okay, it's a law of large numbers argument. Okay, so when n is really big and k is really big, you'll get with n uses of the channel, you'll get n times 1 minus epsilon bits through on average. Okay, so as long as the number of bits you're trying to send, which is r times n, right? As long as r times n is less than 1 minus epsilon times n, then the number of bits that get through will be bigger than the number of bits you've got, and you're fine. Okay, and you can show likewise if r is bigger than 1 minus epsilon, then the error probably will go to 1, in fact. Okay, so that's an asymptotic statement. We also looked at just a very concrete example. We want to send 2 bits, and you get to use the channel 3 times. Okay, so with feedback, we computed the error probability exactly. Okay, and then when we ended last time, we had this very exciting construction here that gave you the same error probability but without feedback. Okay, so you send the same number of bits over the same number of channel uses. And since you have no feedback, you just sort of hard code at the beginning how the data bits get mapped to the channel inputs. Okay, so the way we said to do it last time was you send the 0th bit, send the first bit, and then send the XOR of the 2. Okay, and that way if you have, you can recover from any one erasure, right? If that's erased, you're certainly fine, you got both bits. If that's erased, you're also fine, because you can XOR this with this whole thing, and these will cancel, and you're left with U1. Likewise, if that's erased, from these 2 bits you can recover U0 and U1, right? By XORing this bit with this one. Okay, and 2 bits, you have a half probability of guessing correctly, and if or 2 erasures, you have a half probability of guessing correctly, and then with 3 erasures, you have 1/4. Okay, so it ends up being the same error probability as when you had feedback. And you can't do better than that, right? You can't without feedback only helps. Okay, so you can't do better than this, and we can hit that with this construction. All right, that's where we ended last time. Any questions on this? Okay, so for the whole coding section, I think this example right here conveys like a really key idea, okay, which is that you got to mix the bits if you want to have like optimum recovery from noise. You can't hope to just kind of send the bits in independently and get really good performance. You got to mix. Okay, so this is for 2 bits and 3 samples. Ultimately, you want to scale this up, right? Like lab 4, you got how many? 120,000? No, 200,000 bits to send, okay, and a couple seconds to do it, more or less, right? So that's hundreds of thousands of samples. So how do we scale this up? So first instinct is to just play with examples, right? So do k equals 3 and n equals 5, and do larger and larger examples, look for patterns, okay, and then just try to generalize this. Good luck with that. Okay, people have tried that, and it's hard to find patterns that you can generalize easily. So instead, what people do is something that seems like really off the wall at first, that something that would not naturally occur to a lot of people, but turns out to work extremely well. It's a very powerful idea, okay, which is to just mix the bits randomly at the encoder. Okay, so for each transmitted bit, for each channel use, you just take some random linear combination of the bits you're trying to send, the data bits. All right, some of those linear combinations get through, some don't. The decoder, of course, ignores the erasures, and then among the bits it does get through, it just has a big linear system that it just inverts and recovers the data bits. Okay, and that works, at least in theory, that works as well as coding without feedback. Or sorry, it works as well as communicating with feedback like this. Okay, so you get the same performance as we'll see. Yeah?
How do you know the ordering on the receive side if you do it randomly?
So both the encoder and decoder need to know the randomization. So in practice, you'd use like pseudo-random numbers, and you'd have a seed, and the seed would be hard-coded in both the encoder and the decoder. And then both of them know for each bit that goes across the channel, or the encoder is trying to send across the channel, both the encoder and decoder would know what this is a mixture of. So there's especially the coefficients in the linear system. They both know. Yeah, it's a good question. Other questions? Okay, let me show you how this works. So I give you the basic idea. Let's go through the math. So linear algebra to the rescue again. So we're doing more linear algebra, but this is linear algebra over bits, not real numbers. Okay, so yeah.
I have a quick question about the thing from before.
Yeah.
If you were just solving it as a linear system, why would you have to send them in random order? Couldn't you just send them as was and then solve it? If you're like using the seed to find the order anyway.
So the question is like what for each bit you're sending. So I'm going to explain this in a lot of detail starting right now, but just at a high level, like for each bit you're sending, you have to decide like what the coefficients are in the linear combination, right? So each bit that we send is going to be a linear combination of some of the bits. So in some sense, like here for this one, the coefficients are 1, 0, right? Like 1 for that, 0 for that. Here it's 0, 1, and this is 1, 1, right? Okay, so the question is like when n and k is big, like, you know, how do I decide what numbers to put here? So for this 2, 3 example, I can kind of work out by hand what this should be, but you know, if k is 100,000 and n is 200,000 or something, right? Like it's not entirely clear. Sorry, if k should be smaller than n, right? So k is 20,000 and n is 100,000. You know, it's not entirely clear where I should put ones and where I should put zeros. So the proposal is you just choose all these randomly. Okay, and then let the decoder just solve. You'll get some big linear system with a bunch of ones and zeros in it, and just let the decoder then solve that big linear system. Yeah, so it's not so much the order that the order, I mean, the order is not so important in the sense I could swap these two, right? And the performance is the same. I can swap these two. And the channel just erases each bit independently of the others. So the order in which you send these coded bits, we call them the X's, that really makes no difference. It's more a question of like, what should the coefficients be in this linear combination? And that's what we're picking randomly. Yeah. Other questions? Okay, so it's linear algebra to the rescue again, but it's linear algebra over the binary field. So we're going to do linear algebra in a space where like the entire universe is just 0, 1. Okay, so there are no other numbers except those two. And multiplication is basically doing a logical AND. Okay, and then addition, which I'll draw like that, is basically doing an XOR. Like that. Okay? This is sometimes called the Galois field of order 2, I guess. Characteristic 2, I don't remember the terminology to be honest with you. Anyway, so you can write down like a notion of what a field is. So it's a set of numbers with certain operations, and the operations satisfy certain properties. You know, they're associative and commutative, and you have an inverse, and you have an identity element, and so on for both of these things. So in prior versions of the class, I used to actually write out like what is a field exactly, what are the rules for a field, we check this as a field. I got feedback that there was just a lot of abstract math for not a lot of productive end. So I'm not going to go through all that. I'll just mention that, like, you know, there is a notion of a field in math, and you know, the real numbers constitute a field with the normal multiplication and addition, and so does this. And much of linear algebra carries over to this particular field. Okay, so a lot of the linear algebra you learned in like Math 294 will also work if you just assume everything takes one of these two values, and whenever you have to do multiplication, you use this. Whenever you do addition, you do this. Okay, not all of linear algebra is that way. Determinants in particular get kind of messed up here, in part because like plus and minus are like the same thing. Okay, but a lot of it carries over. So we'll apply that here. So here's the idea. So first pick. So let me give the setup actually. Suppose you want to send k bits over n samples without feedback. Okay. So to do this, we're going to create a random, what's called generator matrix. Okay, I'll call it G, capital G. Okay, it's going to be n by k. So it'll be tall, because n's bigger than k. So G00, G01, G0, k minus 1. And then G10, G11, G1, k minus 1, down to G, n minus 1, 0, G, n minus 1, 1, G, n minus 1, k minus 1, like that. So create this big matrix, and the entries you pick IID Bernoulli half. I'm just going to write B half for Bernoulli 1 half. I probably used that abbreviation before, right? Okay, so you generate this big matrix. It's n by k. N is big, k is big. We might have trouble storing this thing in memory. Let's not worry about that now. Okay, you just generate this big matrix and you populate it with just random entries. Bernoulli half, IID. Yeah, so in practice you'd use a pseudo-random number generator, and the seed would be at both the encoder and the decoder, so both the encoder and decoder know G. Okay, so, all right, and then to encode, we just multiply the U vector of bits by G under this binary field. Okay, so given U, which is a k-length vector of bits, send G times U. Okay, where when you write that, we mean do multiplication and addition like that. So let me do a quick example, make sure we're all on the same page here. Actually, I have a recurring example that we'll use several times, so let me make sure I copy it down correctly. So let's suppose G is the following. So n here will be 7, k will be 4, so G will be 7 by 4. Okay, and the first row is 1, 0, 1, 0. Second row is 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1. This is kind of tight, 1, 0, 1, 1. And then it's 1, 1, 0, 0 way down here at the bottom, if you can see that. Okay. 1, 1, 0, 0 on the bottom, 1, 0, 1, 1 is the second to last row. Okay. All right, and let's suppose the bit string that you want to, the data bits are 1, 0, 1, 0. Okay. So the encoder is handed this bit string, just like your Lab 4 encoder is handed a bit string, has to decide what to send over the channel. Here the encoder is given this, like we want to send these 4 bits. It has to send 7 bits over the channel. Right, so the encoder maps 4 bits to 7. Any valid encoder for this channel, okay, is going to map, at least given k is 4 and n is 7, is going to map 4 bits to 7 bits somehow or another. The way this one works is it just multiplies by this matrix. So you just take G times U like this, and you write it actually as 1, 0, 1, 0. All right, what does that equal? So you use those truth tables over there for multiply and and add, right? So first entry, it's going to be 1 times 1, that's 1, plus 0 times 0, which is 0, plus the 1 gives me 1. 1 times 1 is 1. I add that to this one, I get 0, plus 0 times 0, the whole thing is 0, right? Yeah, you can think of it as and exclusive or if you're like kind of a digital logic, you know, junkie, right? Anyway, so that's 1 plus 1 is 0. The next one is, I mean, you can work all this out, right? Basically, this is just taking the first row, or the first column, and the third column and XORing them, right? You get the second and fourth columns get zeroed out, so it's just this one plus this one. And all the additions modulo 2. So 1 plus 1 is 0, 0 plus 1 is 1, 0, 1 plus 1 is 0, 1, 0, 1. Yeah. Yeah? So that's what it sends, okay? So the encoder just sends this string of 7 bits over the channel, and it's done. Doesn't worry about it anymore. Okay, now the decoder is going to figure all this out. Okay, so it's going to get a string of bits like this, with some of which are erased, right? By the way, what is the, if I interpret this, just back up one moment. This construction, if I express it in those terms, what is G? Here? For this one? Is what?
So it's 1001.
This is 1, 1, yeah. Yeah. This is basically doing addition right here. So this XOR and addition under this binary field is the same operation. Okay, so this encoder maps 2 bits to 3 by basically taking your 2 bits and multiplying by this matrix. Okay, that's what this is doing. So our way of scaling this up, okay, is think of this in terms of a matrix operation like that. Okay, and then rather than trying to figure out what the pattern is, like where to put 1s and where to put 0s, just do it randomly. Okay, just hope it works out. Okay, and it might not work out. Okay, one possibility for G is that every entry is 0. Right, that happens with probably exactly 1/2 to the power n times k. Right, that can happen. If that's your G, you're in a lot of trouble, right? Because the encoder is going to send the 0-bit string. Like if G is all zeros, right? Whatever U comes in, you multiply it by all zeros, you get zeros. Okay? So no guarantee that this is going to work. But let's see. So first of all, let's try just conditioning on it working and decide on the details. So how should decoding operate? Okay, so we have this notation from last time. N was the number of erasures in the channel output Y, right? Number of E's in this string of length N. And let's let L be the opposite, the number of non-erased bits in Y. Okay? And moreover, I'm going to give a name for the indices of the non-erased bits in Y. Okay, so L0 through L minus 1. These are the indices of the non-erased bits. Okay, so mathematically, if you look at Y of Li, that's a non-erased bit. If Y is not erased at one particular instant, it equals X at that particular instant, right? Because this channel never flips bits. It only erases them. So if it didn't erase it, then the output is just equal to the input at that time step. right? For every other index L, Y is at L is just going to be an erasure. So for all L not in L0 through LL minus 1. Okay? All right, our decoder is just going to ignore the erasures, just delete them. Just pretend you didn't even get them. So more precisely, you know, just sort of delete those equations and bits from consideration completely and just assume you had a transmission with L bits where everything got through. Okay, so this is going to form a linear system as follows. So it has a bit for for L0, index L0, for index L1, up to LL minus 1. So those are all the non-erased bits that it's got, right? So put those in a vector. Okay. For each one of these, it's going to equal to x at that time, right? This is x at L0, this is x at L1, and so on. And x of L0, okay, is just g L00, g L01, up to g of L0k minus 1. Times the vector u0, u1, uk minus 1, right? Okay, I know this because x of L0 satisfies this equation. That's how we constructed x of L0. And L0 is a non-erased bit, therefore y of L0 equals x of L0. Okay, so you take in terms of this example, you take this vector, you feed it through the channel erases certain bits and not others. The ones that are erased, just delete them and shrink the dimension, okay? And then just shrink all the rows of G, eliminate all the rows of G that corresponded to erased symbols, and you just have a reduced dimensional system. Do you have a question?
Can the input be reduced to L size as well?
No, because so I can maybe kind of explain this on two levels. One is like you want to solve for all the bits. So if you start deleting bits, then you're not going to be able to solve for them. But another way of looking at it is like over here, you know, when the channel erases a certain bit, it's like that whole equation just didn't happen like that. So you know, the dimension of this thing stays fixed, and you're just shrinking this in this dimension here. So certain bits get erased that way. Yeah. Other questions? All right, so just filling this in. So GL10, GL11 through GL1k minus 1. And then the last row is G of L minus 1, 0. G of L minus 1, 1. G of L minus 1, K minus 1. Yeah. Okay, so these are all known, right? These come out of the channel. So I have concrete numbers to put here. These are all known too, right? I know the G matrix at the decoder, and I know which indices got through and which didn't, so I know all these L's. So I know this vector, I know the matrix, I don't know this, right? I have a linear system of equations, right? Capital L unknowns, capital L equations, K unknowns. If I handed this to you, how would you solve it? What would you do? Sorry? MATLAB? And what would you do in MATLAB? Yeah.
Multiply your received vector by the inverse of G.
Well, G, you know, this is not really G. Let's give this a separate name maybe. this matrix that's called G prime, and observe G prime is not G, right? G prime is G with a bunch of rows deleted. No guarantee that G prime is square. G is usually not going to be square. It's usually a very tall thing. You're usually mapping a few bits into many samples. Otherwise, if you want any hope of recovering the bits, it's got to be that way. G prime, in practice is usually like slightly tall, but still tall. Yeah.
Does this matrix have some property? Is it like unitary or something that we can like?
Well, it's random,
Okay.
right? So there's some probability it has some property, right? There's another probability it has, actually, I mean, fully random matrices tend to be rather, I wouldn't say structureless, but I mean, if you just pick so here it's binary, but if you have like a 4x4 matrix and you just pick like the components as i.e. Gaussian, like the chance it's unitary is essentially 0, right? Because I mean, the chance that like two vectors are exactly orthogonal, it's a 0 probability thing, right? So yeah, no structure. I think you guys are overthinking this. Just a little, yeah. It's called Gaussian elimination, right? Right. Just it's a linear system. Like you guys are thinking in terms of like undergraduate engineering. Like this is like a high school or level exercise, right? In principle, okay, you can just solve it using Gaussian elimination. Okay, I'll use our script N for an abbreviation for Gaussian. So let me do an example of this. Oops. You want me to do a quick example of Gaussian elimination with reals first, or should we jump straight to the binary thing? Binary? Okay, all right. Okay, so let's use the same G. And let's suppose you receive 0, 1, wrong sheet. Okay, 0, 1, 0, 0, E, 0, E. Okay, so you're staying to the decoder side, you know the G matrix, and this is what pops out of the channel. Okay, so you know the channel's erased a couple of symbols and it's let all the other ones through, and now we got to figure out what U was. Okay, so if I try to do this by erasure on this G that's already up here, maybe not because I've already kind of disturbed it. Okay, so let's first write out the system like we have it there. So I can't see. So 0, 1, 0, 0. E, 0, E. Is that what that says? Okay, so that's my Y. And then, okay, I shouldn't have erased the G, even if I was going to recopy it. So what was my G? So there's a bunch of things. Sorry. It's a bunch of things. So actually, okay, if I want to do it in the form that I wrote up there, you don't put the E's, right? So just drop the E's. So I have 0, 0, right? I have a vector of length 5 by dropping the E's, okay? And then the G prime is G with the rows corresponding to the erasure is gone. So the bottom row and the third row from the bottom both dropped, and we save all the other ones. Okay, so we're saving 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, and 1, 0, 1, 1. Right? Okay, and from that data, we want to estimate these 4 variables, U0 through U3. Okay, so just solve this the way, do you have a question? Okay, so just solve this the way you would a linear system from high school. Okay, so this is basically Gaussian elimination. So I'm going to take the first equation, and I'm going to clear these ones by adding this equation to this one and replacing it. So replace this equation with this one plus this one. Okay, so in that case, this one annihilates this one, we get 0. This one annihilates this one, we get 0. And 0 plus 0 is 0, so that stays 0. Likewise, do the same thing. Replace this equation by this equation plus the first one. So the 1 cancels that one, 0, like that. Okay? And then what else? So you can add this. I'm going to use a different color. Add the second equation to the third one and the fourth. Right? So replace both the third and the fourth with that equation plus the second one. So this becomes a 1, that becomes a 0, this becomes a 1, right? And likewise, okay, this is getting kind of confusing. So if I add the second equation to the fourth and replace the fourth with that sum, this is going to become 0, this is going to become 1 again, this is going to become 1. Okay? Anyway. You get the idea. Solve and eliminate. So anyway, we should be able to just write down at this point what things are, right? So U3, if you look at the bottom line here, this is just reading U3 equals 0, right? The second, U2, if I look at this equation right here, it's reading U2 equals 1, right? What else can I do? I know that U0 plus U2 is 0, and U2 is 1, so U0 must also be 1. And what's left? U1. I need an equation for U1. This has U1 in it. And U1 plus U2 is 1. U2 is 1, so U1 must be 0. So I get 1, 0, 1, 0. That's my guess for U. Is that the U I encoded? I erased it now, but yeah, okay. All right, so we did it right. Okay, so actually this is in some ways easier than, I'm sorry, this is a little bit busy with all these colors, but it's actually easier than when you're dealing with real numbers, because when you deal with real numbers, you might have like a 1 here and a 3 here, so you got to multiply this by 3 and then subtract it from that to clear to give you a 0. Whereas in the binary field, like the only non-zero thing you can multiply by is 1. Okay, so you don't multiply these things by anything, you just add them. Okay, so just take one equation and just XOR it with other equations to kind of clear ones to give you a upper triangular shape. And once you have an upper triangular shape, then you can start substituting variables in and pick them all off. Okay? So, so you can show this works. I won't prove it. The proof is like essentially the same proof for real numbers, so there's not a whole lot of point in going through it. So by works, I mean it will never spit out the wrong value for U. Okay, it can very easily terminate prematurely and say you don't have enough equations to solve this. Okay, that can happen, but it will never give you an incorrect guess for U. Okay, so this is Gaussian elimination. So Gaussian elimination. Never outputs an incorrect guess for U. It may terminate prematurely. Okay, even if G is a great matrix, even if the G that you got is, perfectly good, it can happen, the channel erases everything but one equation, and now you're trying to recover k bits, like k variables from one equation, so it's not going to happen, right? Clearly, if you have any fewer than k equations, there's no hope of inverting this, right? So it may terminate prematurely, meaning it just says you don't have enough equations to solve for all these variables. It will output a guess if G prime, this matrix, the one that's reduced by the erasures, if G prime has full column rank, okay, meaning there doesn't exist a non-zero vector in its null space. There does not exist v not equal to the 0 vector such that G v is equal to 0. Okay, it's not hard to see that if there is such a v, then you have no hope of uniquely identifying the u over here, because any vector, if one vector is a solution, the vector plus v will also be a solution. And you can also show that if there's no such v, then there's a unique solution. Okay, so we still haven't answered the question of whether this really, works, and that, like, what kind of an error probability would you get? I mean, there's a lot of things that can go wrong with this, right? You can have too many erasures. The G could be bad. Sure, I mean, the decoder can try to solve Gaussian elimination as best it can, but, I mean, it might be that it just never really works in practice. In practice, it just always terminates prematurely, right? So let's look at the error probability analysis. So first we have to understand what can we say about these random matrices. I generate G, IID, Bernoulli. Okay, the rows get deleted by the channel when it erases things. I end up with a G prime matrix, like here I just had. What's the chance that the G prime matrix has full column rank? That's basically the error probability. Let's just start with a fact about random matrices. So suppose, I'm not sure what to call the matrix A. I suppose we have a matrix A, and it's got alpha n by beta n components. People know this floor notation. I don't know if I've used this yet in this class. Floor is like, it's like rounding, but you always go down, at least with positive numbers. Okay, so 1.5 gets mapped to 1, 1 gets mapped to 1, 1.9 gets mapped to 1, 2.1 gets mapped to 2. Okay, like rounding, but don't go up, always go down, or towards 0 anyway. Okay, so suppose A is a binary matrix with this dimension. Now let's suppose its components are IID Bernoulli half. So A is a random matrix. Okay, I have all these slots, alpha n by beta n. Okay, I generate a bunch of IID Bernoulli 1/2 random variables. I put those in the matrix. I'm going to consider the chance that A has full column rank. Basically saying the columns are linearly independent of each other. Okay, i.e. there does not exist a V like this. It's basically saying the columns of G are linearly independent, right? Okay, we're going to consider this probability in the large N limit. Okay, I claim it equals 1 if alpha and beta satisfy a condition, namely 1 is bigger than the other. So which is it? But bigger, less. What do you think? Okay, so alpha and beta are fixed, maybe I should say at the beginning here, fixed alpha and beta positive numbers. Okay, I generate a big matrix. It's alpha n rows beta n columns, right? Alpha n by beta n. We just fill all this with ID Bernoullis. You get this big binary matrix, okay? I'm claiming if you scale it up, so the ratio, the number of rows to the number of columns is fixed, okay? So you have like a box of a certain size, or you take a certain rectangle, and then you just grab it by the corner, okay, and just grow it. Okay, so the relative size of the edges remains fixed. We blow this thing up. Okay, I claim in that large n regime, the chance this thing has full column rank tends to 1 if alpha and beta satisfy some relation in relation to each other. And what is it? Alpha greater than beta, exactly. Okay, so alpha bigger than beta means you're looking at matrices that are tall, like that, right? It's alpha bigger than beta. The other way around, fat. Okay, you're not going to get linearly independent columns like that, right? You got too many of them, and the dimension's too small. You can have linear independence with columns like that, though, right? That doesn't. This reasoning does not prove this is true, okay? But it certainly indicates that you would not expect this to be true with the inequality going the other way. All right. Proof of this is one of the next homework problems. It's not nearly as daunting as it looks. Okay, you just do a union bound over all possible v's. Okay, so there are 2 to the beta n different v's. Okay, each one has a probability 2 to the minus alpha n that it gives rise to the 0 vector when you multiply it. So just union bound, multiply those 2 together. That's it. It's like 3 lines or something. Okay, so it's not. It looks scary, but it's actually not that much work to show that. Okay, so with that, we can now analyze the error probability. Okay, so we'll get the chance that at least one of the k bits is decoded incorrectly, so it was wrong. In order for that to happen, the G prime matrix has to be not full column rank, right? Because if it is full column rank, then Gaussian elimination will work. It'll spit out an answer, and that answer is never wrong. Okay, so in order to get an error, we need G prime to not be full column rank. Okay, and there's sort of like 2 ways errors can happen on some level. Like, I mean, in reality, there's like one way, which is that G prime, is not full column rank. But there's sort of 2 underlying sources of that error. One is the channel erases too much. Okay, and the other is that the G matrix was just bad. Okay, like, G can be just like a really low rank thing, in which case, like even if the channel erases about as many as you expect it to, you still have a problem. Or you can have the channel can just erase like a lot more symbols than you wanted, and then even if your G is good, then that would cause an error too. Turns out it's helpful to split those 2 cases out. So I'm going to write this probability as an intersection with an event and its complement. So we're going to look at how many symbols get through. Remember, L is the number of non-erased bits. Okay. So we're going to compare that to a number I'm going to choose very carefully here. The arithmetic mean of the rate and 1 minus epsilon. And then we'll probably do the same thing intersected with the complementary event. So that's certainly true, right? Probability of A equals probability of A intersect B plus probability of A intersect B complement. Okay, that's all that is. Okay, now for the bottom event, I'm going to take an upper bound here by just deleting this. Just save this part. Right? Probability of A intersect B is upper bounded by probability of B alone, right? And I want upper bounds here on the error probability. We know it's lower bounded by 0. I want to show it's upper bounded by something close to 0. So we want upper bounds. I'm going to get an upper bound by just dropping the rank thing and just save the L. Okay. So I'm going to show the error probability goes to 0 under the same condition it did with feedback. So let's suppose now that n and k go to infinity, with r being the ratio fixed, and r satisfying the same condition that we had with feedback. So r is less than 1 minus epsilon, like that. Okay? Let's look at that second probability there. It's probably that L over n is less than 1 minus epsilon plus r over 2. Okay? This is going to go to 0 by law of large numbers argument. R is less than 1 minus epsilon. Okay, and 1 minus epsilon is the mean of L over n. So let's write this out more carefully. So remember we did the law of large numbers argument last time. We had a z variable for each output symbol to record whether it was erased or not. Right? The z's are IID. Let's actually flip this. Is that OK? It's going to just easier for this argument if we flip it. So it'll record which bits got through. OK, so then L over n is the arithmetic mean of the z's, right? Okay, so what we're left with, not what we're left with, but in those terms, this probability here is the chance that 1 over n running sum of the z's less than or equal to 1 minus epsilon plus r over 2. Okay, and this quantity here, this is strictly less than 1 minus epsilon. Okay, because it's the arithmetic mean of 1 minus epsilon and r is strictly less than 1 minus epsilon, right? So this thing is strictly less than 1 minus epsilon. Okay, so now this random variable is concentrating around 1 minus epsilon, right? The mean of each zi is 1 minus epsilon. So this running average here, by a law of large numbers, it concentrates around 1 minus epsilon, and this number is below that, and we're asking a chance it's below that threshold, right? So the picture to have, the mean is here. It's becoming more and more concentrated around the mean. Right? And then the number we care about, 1 minus epsilon plus r over 2 is way out here. Right? So this thing concentrates around 1 minus epsilon. So the chance it's below that number, that goes to 0. As n goes to infinity. Or as n and k go to infinity together. Okay, so that's this term right here. This whole second term, this one, we just showed this went to 0. Right? That's what we just showed. Let me work with this one now. The first term. Okay, so for this, we'll use the fact that if you have a matrix that's not full column rank and you delete rows, then the new matrix is also not full column rank. Okay, so linking to this, since that probability involves a lot of writing, let me just use an arrow here. Okay, so here's the reasoning. So if G prime is not full column rank, and it has more than this many rows, more than, L is the number of rows that G prime has, right? Okay, so if G is not full column rank, and it has more than 1 minus epsilon plus r over 2 times n rows, okay, that means any submatrix with exactly 1 minus epsilon plus r over 2 times n rows will also not have full column rank. So just take G prime, delete rows until the number of rows remaining is this thing times n. that will again not have full column rank. So this thing is upper bounded by the chance that a 1 minus epsilon plus r over 2 times n by nr matrix with ID Bernoulli 1/2 entries. Is not full rank. Okay, and from our fact that we're just up here on this board, part of homework 7, okay, this goes to 0 as n goes to infinity, so long as the matrix is tall, meaning this quantity exceeds that one. So as long as 1 minus epsilon plus r over 2 greater than r, and that's equivalent to r less than 1 minus epsilon, right? Which is exactly what we're assuming. Okay, so this first event also has a probability that goes to 0 so long as r is below 1 minus epsilon. Okay, and just to link it back, remember the condition r less than 1 minus epsilon, this condition right here, this was exactly the condition we needed for the scheme with feedback to have a vanishing error probability as n grows, right? When we did the feedback case, we said the error probability there will go to 0 so long as the rate is below this threshold, okay? So this is showing if you do this scheme with the random matrix without feedback, the error probability will go to 0 under exactly the same condition. Every rate you can handle with feedback, you can handle with this scheme too. So in terms of rate anyway, in terms of what rates you can sustain with really low error probability, makes no difference whether you have feedback or not, okay? In terms of computational complexity, that's a very different story, okay? But just if you ignore computational complexity, just think about the data rate and like how much can you recover from the stochastic errors introduced by the channel, feedback or not, okay, it's the same condition. So I'd say this works. I'd say this works remarkably well, actually, okay? And it's easy to get lost in the math, especially if you want to go through the proof carefully that the error probably goes to 0 under this condition. The rough idea, the very intuitive idea here is that the encoder just kind of sends random linear combinations of the data bits. The decoder then gets like, one linear equation for each non-erased bit, okay? Since those coefficients are chosen randomly in the G matrix, these equations tend to be linearly independent. Not guaranteed to be, okay, but they tend to be, all right? And so if it gets 1 minus epsilon n equations, and it has r variables to solve for, so long as r is less than 1 minus epsilon, it'll tend to be able to invert this thing, okay? Note that when I write error probability here, when I write this, I did something kind of slick here. So this PE, there's kind of two sources of randomness here, when you write here. This P, there's two sources of randomness, right? There's the random erasures in the channel, and there's the randomness in the G. And this P encompasses both. If you look at the way this computation is done, it's implicit that both forms of computation are being considered here. Okay, so one way in which this can happen is that the G is just like all zeros. Another way it can happen is that the channel erases everything. Okay, and there are lots of other scenarios in between. Okay, but this is not just the channel randomness we're talking about here. It's also the G. Okay. So in practice, this says even when you choose G randomly, like my experiment is, I choose G randomly, I hard code that in both the encoder and the decoder. I get K bits, I feed that into the encoder, the channel erases some, I go and do my Gaussian elimination, I look at what comes out, I compare that to the original data bits. Okay, this calculation is saying when all that is said and done, okay, when n and k are big, so long as r satisfies this condition, the chance the decoder gets the bit string wrong is small. Okay, so in particular, the chance that the G matrix is bad is also small. Okay, so in practice, if you want to do this, just generate a few seeds for your pseudorandom number generator. For each seed, just try it. Okay, eventually you got to find a seed that works. Most seeds will work, in fact, okay, because this error probably is going to 0. Okay, so just find a seed that works well. Just hard code that in the encoder and decoder. That's it. Okay. Conceptually, anyway, that's it. Let's talk about complexity. If we were to actually implement this, what's the story? Any questions about this analysis? The really key step in the proof is to kind of divide the analysis in these two cases. Like the channel eats too much and the channel doesn't eat very much, but the G matrix is bad. You got to kind of split those two events out rather than trying to deal with it as just one scenario. Okay, complexity. For the encoder, in terms of n and k, what's the rough order of the complexity? What's the encoder doing again? Multiply by matrix. How big is the matrix? N by k, right? So like n times k complexity, and k and n are the same order, right? They're proportional to each other, so we'll just say n squared, right? Decoder. Okay, so if I have n equations and n unknowns, and I do Gaussian elimination, what's the complexity in n? Any ideas? More than that. I mean, just multiplying gives you the square, and you're doing a lot more than that. Sorry?
You need to actually solve, so it's more than n squared.
More than n squared. How much more?
N squared log n.
Yeah, it's n cubed, actually. It'd be nice if it were n squared. N squared log n is just like log n, right? I've been in, I didn't have a comic relief. Actually, I didn't have it on my science today at all. I didn't have a planned comic relief, but I was at a research talk one time where someone had, it was a coding scheme, actually, for binary channels like this. It works for the binary Azure channel. And the complexity was n log n. And the speaker said, what's the factor of log n among friends? Right? It's basically just linear, right? So yeah, log n is almost just like a constant you can absorb in front. So if you do just like a regular implementation of Gaussian elimination, then you'll get n cubed, because what will happen is like, so first thing you do is you want to clear like all these entries, replace them with zeros, right? So you're going to take this row and then like, you know, scale it and subtract, right? So just to clear these entries here to get zeros in this first column, you have to kind of pass through the whole matrix, right? So that's n squared complexity right there. And now I gotta do the same thing here, right? So now after I do that first step, I'd have 0, 0 like this. Okay, and now I want to clear this 0, right? So you gotta take this row and then scale it and subtract here to give that. So maybe a 3 by 3 is not a good example, but you know, for each column, you end up kind of passing through most of the matrix. So you get n times n squared complexity. Okay. Do you like? Not like? Is it obvious? This is no good, right? This is like way too big. This is way too big. Okay, this is also not really workable. All right, so great idea in theory. An extremely powerful idea in theory. In practice, you can't quite do it like this if you want to scale this up. I mean, you need k and n to be large for the law of large numbers to kick in. See, all this error probability analysis was based on the law of large numbers kicking in, right? So we need, here was an explicit law of large numbers invocation right here. There's sort of an implicit one underpinning this, right? So you need n and k to be big for the error probability to be small, because you're kind of relying on the fact that the channel doesn't erase more than n times 1 minus epsilon of the symbols. So that's only true in the kind of large n regime. So you need n to be big, but if n's big, then like you can't even store these matrices in memory anymore, right? Much less try to do Gaussian elimination and multiply. Okay, so there are some tricks you can use to pull the complexity way, way down. In fact, get this down to something that's workable. And I won't. We're going to start down that path. We will not go the full way, however. I'm just going to give you a kind of a flavor of how that works. Because very quickly it starts getting kind of specialized to the binary Azure channel. This is not really the channel we care about in the end. So I don't want to get too deeply into this. I just want to give you a sense of what you can do. So let's work on the decoder first. The decoder is the worst of the two, right? I mean, they're both bad, okay, but the decoder is worse. So let's think about decoding first. And I'll show you another algorithm for decoding. It's not as good as Gaussian elimination, but it's a lot faster. Okay, and if you design the encoding well, it can turn out it works almost as well in practice as Gaussian elimination. Okay, so this is called peeling. It turns out to be equivalent in this particular case to belief propagation. Anybody heard of belief propagation? Really? No? Oh, wow. It's a big concept in machine learning. Well, it's a big concept in many fields, but it crops up a lot in machine learning. And I hear students are big into machine learning these days. I guess maybe you're not. That's why you're here, right? Anyway, if you take a class on like graphical models and so on, you'll talk a lot about belief propagation. And I don't want to get into what belief propagation is in this class. It's a whole topic unto itself. But if you know what it is and you apply it to this problem, okay, then it reduces to the following algorithm I'm going to describe. So let's start with Gaussian elimination first. And I'm going to describe the Gaussian elimination as like a two-step operation, the second of which repeats. Okay, so first step, I'll say put the matrix in your linear system in row echelon form using row operations. So like, triangular form, basically. Well, it's not necessarily square, but okay. And then second of all, you look look for a row or an equation with only one variable present in it. So like basically one row in the matrix that has one non-zero entry in it. Solve for that variable, which just amounts to reading it off, okay, because it's the only variable in that equation. Eliminate that variable from all others. From all other equations, that is. Okay, and then repeat. So go to 2. At that point. Okay, so you put it in, you get the matrix in like diagonal form. So in a 3x3 case, these dots are just like numbers here. You're trying to solve a linear system like that. So after the first step, the first step is you do row operations to get it in row echelon form. It looks like this. Okay, you look for a row with one non-zero entry in it. That's here. That allows you to just pick off one variable, or you read off one of the variables, and then you can eliminate that variable from other equations. Once you eliminate that variable from this one, now this one only has one variable left, so you can just read it off, eliminate it, read it off. Eventually, you've got all of them. Okay, so that's Gaussian elimination. So peeling is just a slight tweak on this. Skip 1. That's it. Just proceed directly to 2. And just keep repeating 2 through 5 over and over again. Okay, so I'll do an example of this. Actually, do I need to do an example? Is this pretty clear? I shouldn't ask two questions that are opposing, because people say yes, and I don't know which question they're saying yes to. So would you like me to do an example of peeling? Yes, okay, thank you. Okay, so find a row with 1, 1 in it and use that to read off one variable. So this last equation says u2 equals 1. Okay, I then eliminate that from the other equations, and it's not appearing in the second equation already. Here I'm going to subtract u2 out. And my new system is going to be 1, 0, 1, 1 equals 1, 1, right? Like that. From this I can read off that u0 has to be 1 as well. Okay, and then if you substitute that into here, you get that u1 must be 0. So 1, 0, 1 is the solution, okay? So the point is you skip the row echelon thing in the beginning. Just hunt for, one equation that just has one variable in it, read it off, just back substitute, and just keep repeating, okay? So again, this will work in the sense that it never spits out the wrong answer. It never gives you an incorrect guess for you. It can terminate prematurely, and it's much more likely to terminate prematurely than Gaussian elimination is. Okay, so here's a fact. So peeling never outputs an incorrect guess for you. It may terminate prematurely. If it outputs a u, then Gaussian elimination will output the same u. Okay, so the difference is, Gaussian elimination will only terminate prematurely if your linear system is just not solvable. Okay, if you just have not enough equations, or you have redundant equations or whatever. Okay, if there is a unique solution to the linear system, Gaussian elimination will find it. No guarantees with peeling. Okay, if it finds a solution, it's guaranteed to be the right answer. It will never give you the wrong answer. Okay, but it can easily terminate prematurely, even if the system is solvable. Okay, in particular, to get off the ground, the linear system has to, at the get-go, have at least one equation with only one variable in it. Right? Your G prime has to have at least one row that has a single 1 in it. Okay, and you can easily construct examples, okay, of channels where, like, if I put a 1, I don't know, here maybe. No, that would be. Anyway, I'm going to try to construct an example on the fly. You can usually construct an example of, like, even a 3x3 matrix where it's solvable. Okay, the equations are linearly independent, but there's no row with a single 1 in it. Okay. In particular, if n and k are big, and you generate the rows I, D, Bernoulli half, okay, how many rows are you going to have with like 1, 1 in them? Roughly 0. Okay. The chance of any one single row being all zeros is going to 0 exponentially and fast, and you only have linearly many rows, right? So it's like n times half the power n. That's the chance that you have at least one. That's the chance you have at least a row with all zeros in it. And the chance you get 1, 1 is close to that. Okay. So this will run faster. We will do some complexity analysis. So I didn't quite finish this topic today. We'll do some quick complexity analysis on next week. I'll show you the graph way of doing this. If you get more deeply into coding theory, you'll see this is often done with graphs instead of matrices. There's a reason for that. I'll show you quickly the graph way of thinking about this. Say a few words about random coding, like how to generate G prime or how to generate G so that this peeling thing works out. And then we'll start talking about coding for the ComCloud channel. Okay, so I have office hours now if you want to talk about the homework or whatever, and I'll see you Tuesday.